All right, so here we have kind of a complicated system here. Okay, we've got two connected blocks and a pulley. In this case, this isn't a massless frictionless pulley. This is a pulley that has mass. So we have to consider when we're talking about it. What we're looking to find is what is the acceleration of the two blocks. Now this block is 1 kilogram and it's sitting on a table that has a coefficient of friction of 0.2. The pulley has a mass of 0.5 kilograms and a radius of 10 centimeters. Make that a little bigger. Okay. The lower block has a mass of 0.5 kilograms. So starting out, we've got to again go with our forces here. Okay? This guy's clearly going to have a gravitational force of 0.5 times 9.8 equals 4.9 newtons. Up here, we've got a force, a frictional force going the other direction, right? And the frictional force is going to be 1 times 9.8 times 0.2, or 1.96 newtons, which gives us an overall net force of 2.94 newtons. Alright, so that part itself doesn't have anything to do with the pulley. But now we have to consider the fact that the pulley has to be accelerated so that the string is accelerated at the same speed for both the block, the pulley, and the other block. Okay? So, that makes sense. I'm going to take a second here and call this block A. Okay? This is block B and that's the pulley. So what we know is that the forces exerted on block A plus the forces exerted on block B plus the force exerted on the pulley is all going to add up to F net, or 2.94 newtons. Makes sense, right? Now we also know that all three of these things have to have the same linear acceleration, which is easy for FA and FB. That means FA over the mass of A equals FB over the mass of B, which is equal to something about FP. But we're going to take a second here to figure out what that is for FP. Now what we want is the angular acceleration of P to be equal to be in such a state where the angular acceleration of it is giving the string the same linear acceleration. Now it turns out if we multiply that times r, we get A. Right? Now angular acceleration is going to come from torque. We actually know that torque T over I equals alpha. We also know that torque is equal to the force of the pulley times R. So we plug all that in, we get that A for the pulley, okay, is equal to F of the pulley R squared over I. So we know that's also equal to F pulley R squared over I. Now, this point we should probably find out what I is. Okay? I is going to, for a pulley, is the same as for a disc, and it's 1/2 m r squared, which is going to be 0.25 times 0.1 squared, or 0.0025. We then plug that back in here, and we get that's equal to F pulley times 0.1 squared over 0.0025, or 4 times F pulley. Now, with that, we can then plug stuff back into here. Okay? We get FA plus, we can substitute an FB here. I'm going to take a second here and erase MA and F, the mass of each one. This is going to be 1, this is going to be 0.5. Okay? Means this is 2. FB is going to equal twice FA. And FP is going to equal 1/2 FA. And all that's equal to 2.94 newtons. We solve that for FA, and we get FA is equal to 0.84 newtons, which also tells us that the acceleration of A is 1.68 meters per second squared. Now, if we solve for the other ones, we get that's the same acceleration, which is good for all, because they all should be the same, and because they're connected. And that is the acceleration of the blocks.